Hello friends, today we find the formula for transverse acceleration. So first we suppose that there is a moving particle which moves on a curve. Let a moving particle which moves on a curve which moves on a curve and it is at point P at time t, and at time t plus del t it is at point Q. Here we can see that there is a moving particle which moves on a curve. Suppose that the particle is at P point at time t. After del t time, the particle reach at point Q. Suppose this is the Q point here and this is the pole here. OX is the initial line. Let us suppose that there is a particle which moves on this curve at time t. The particle is at point P. After del t time, that means at time t plus del t, the particle is at point Q. We suppose that the polar coordinate of P point B are theta. So the radius vector OP is equal to small r and the vectorial angle XOP, this is equal to theta here. So this angle is theta. Here the polar coordinate of P point B are theta. So the radius vector OP is equal to small r and angle XOP, this is equal to theta. We know that the velocity along the radius vector OP, this is called radial velocity, which is denoted by a small u. Here u is the radial velocity along the radius vector OP. Here u is the radial velocity along the radius vector OP. And OP is the radius vector which is equal to r, angle XOP, this is equal to theta. Also we suppose that the polar coordinate of point Q be r plus del r and theta plus del theta. So the radius vector OQ is equal to r plus del r and angle XOQ, this is equal to theta plus del theta. Here we suppose that the polar coordinate of this point Q is r plus del r and theta plus del theta. So OQ radius vector is equal to r plus del r and angle XOQ, this is equal to theta plus del theta. Now we find the angle POQ. So angle POQ, this is equal to angle XOQ minus angle XOP. So angle XOQ is here theta plus del theta and angle XOP is theta here. So theta is cancelled out. So this is del theta. Here we can see that this angle POQ is equal to angle XOQ minus angle XOP. XOQ is here theta plus del theta and angle XOP is theta, so theta is cancelled out, so angle POQ is equal to del theta. Here we can see this angle is del theta here. We know that the radial velocity along the radius vector OQ is u plus del u. Here we suppose that the radial velocity along the radius vector OQ is u plus del u. And we know that the velocity component which is perpendicular to the radius vector OP at point P is transverse velocity. So here V is the transverse velocity. We can see here this velocity component V is perpendicular to the radius vector OP at point P. So this is the transverse velocity at P. Here V is the transverse velocity at P, which is perpendicular to the radius vector OP. Similarly, we can see here the velocity which is perpendicular to the radius vector OQ is transverse velocity. This is V plus del V. Here we can see that here at P point V is the transverse velocity which is perpendicular to the radius vector OP. Here V plus del V is the transverse velocity at Q point which is perpendicular to the radius vector OQ, and this angle is 90 degree here. Now we can draw a line which is parallel to OP going from, suppose that this is the line, suppose here we draw a line which is parallel to OP. Suppose this is M and this is N point. So this is MQN is the line here. Draw MQN parallel to OP. We know that this angle is also del theta because this del theta and this angle both are corresponding angle. So this del theta, so this is also del theta. Now we find the component of U plus del U in the direction of Mn. So we get here U plus del U cos del theta. This is the horizontal component of the radial velocity U plus del U in the direction of Qn. Now we can see here this angle is 90 here. Now we can see here the transverse velocity at here we find component of U plus del U. Here we find component of U plus del U which is perpendicular to MQN. So we find here this is the vertical component of U plus del U which is perpendicular to the MQN. So this angle is here, this is 90 degree because this is perpendicular to MQN and this is del theta. So this becomes here we find this angle is 90 minus del theta. This is 90 minus del theta. And we know that this angle is 90 degree This is 90 degree and this is 90 minus del theta. So this becomes del theta, because when we subtract 90 minus del theta from 90, we get this is del theta. So the velocity component, transverse velocity component v plus del v along this perpendicular line is v plus del v and cos del theta. And this component of v plus del v, component of v plus del v along this qm is v plus del v sin del theta. Again we explain this figure. Suppose that there is a particle which moves on this plane curve. At time t, we suppose that this particle is at point P. After del t time, that is at time t plus del t, the particle is at point Q. We suppose that the polar coordinate of P point B are theta. So the radius vector OP is equal to small r and angle XOP, this is equal to theta. We know that the velocity along the radius vector OP, this is called radial velocity, which is denoted by small u. And the radial and the velocity component which is perpendicular to the radius vector OP at P point, this is called transverse velocity, which is denoted by small v. So v is the transverse velocity at P point, which is perpendicular to the radius vector OP, and u is the velocity along the radius vector OP here, and u is the radial velocity, where v is the transverse velocity component. Now at Q point, the velocity along the radius vector OQ is u plus del u, and u plus del u is the radial velocity. Whereas at Q point, the velocity component which is perpendicular to the radius vector OQ is v plus del v, and this v plus del v is the transverse velocity, because this is in the direction perpendicular to the radius vector OQ. Now this angle is 90 degree, you can see here. Now we draw a line MQN which is parallel to the radius vector OP. Now you can see this angle is del theta, so this is also del theta, because these are the corresponding angle. So this is del theta and this is u plus del u. So component of u plus del u along Qn is u plus del u cos del theta. This is the horizontal component of the radial velocity at point Q. So the component of radial velocity u plus del u along Qn is u plus del u cos del theta. Now we find the velocity component of u plus del u at point Q in perpendicular direction. So this is u plus del u, we find here the component of u plus del u. So this is u plus del u and sin del theta. You can see here component of the radial velocity u plus del u along Qn is u plus del u cos del theta. This is the horizontal component. And the vertical component of u plus del u along this perpendicular line is u plus del u sin del theta. Now we can see here this whole angle is 90 degree and this is del theta. So this angle becomes 90 minus del theta. And here we can see that this is the radial velocity u plus del u, and this is the transverse velocity v plus del v, and we know that angle between the radial velocity and the transverse velocity is 90 degree at point Q, and so this is 90 minus del theta and this is 90 angle. So when we subtract 90 minus del theta from 90, we get del theta. So this angle is del theta. Now we find the component of transverse velocity v plus del v along this perpendicular line is v plus del v cos del theta. This is the horizontal component of V plus del V along this perpendicular line. And component of V plus del V along this is QM V plus del V sin del theta. So now we find the radial. Now we find the transverse acceleration. Now we find the transverse acceleration. So we can see here. Now we can see here. We find here transverse acceleration. Here we find here transverse acceleration. This is equal to limit del t tends to 0, change in velocity perpendicular to radius vector in time del t divided by del t. We know that acceleration is the rate of change of velocity. So here transverse acceleration is the limit del t tends to 0, change in velocity perpendicular to radius vector in time del t divided by del t. We know that change in velocity in perpendicular direction, that means final velocity minus initial velocity, that is velocity at point Q minus velocity at point P. So velocity at point Q in perpendicular direction to the radius vector is, we can see here, u plus del u sin del theta plus v plus del v cos del theta minus v divided by del t. You can see that the velocity component at P point perpendicular to the radius vector, perpendicular to the, here we can see the velocity component now we solve this. So we can see here limit del t tends to 0, u plus del u, and sin del theta is 1 minus del theta whole cube upon 3, here del theta minus del theta whole cube upon factorial 3 plus del theta whole power 5 upon factorial 5 minus, and so on, plus v plus del v, and cos del theta is 1 minus del theta whole square upon factorial 2 plus del theta whole power 4 upon factorial 4, and so on, minus v divided by del t. So neglecting powers of del theta, we get here limit del t tends to 0, u plus del u and del theta plus v plus del v and 1 minus v divided by del t. Now again we neglect this product of del u and del theta, so we get u del theta plus v plus del v minus v divided by del t. We can see that this v's cancel out, so limit del t tends to 0, u del theta plus del v upon del t. Now we bifurcate this, so we write this u del theta upon del t plus del v upon del t. Now we taking limit, so we get here u d theta upon dt plus dv upon dt. We know that u is the radial velocity which is equal to dr by dt, and v is the transverse velocity which is equal to r d theta upon dt. Now we solve this. So we get here dr by dt multiplied by d theta by dt plus, here we differentiate, we use product rule of differentiation. So first function r d by dt of d theta by dt plus second function and differentiation of first, so dr by dt multiplied by d theta by dt. So this is dr by dt multiplied by d theta by dt plus r, and differentiation of d theta by dt with respect to t is d2 theta by dt2 plus dr by dt multiplied by d theta by dt. Now this can be also written as r d2 theta by dt2 plus 2 dr by dt multiplied by d theta by dt. So this formula can be written as this is the transverse acceleration r d2 theta by dt2 plus 2 dr by dt multiplied by d theta by dt. Now we can see this formula can also be written as 1 upon r times r square d2 theta by dt2 plus 2r dr by dt multiplied by d theta by dt. So this is 1 upon r and d by dt of r square d theta upon dt. So we know that transverse acceleration of a moving particle can be evaluated from this formula 1 upon r d by dt of r square d theta upon dt. Thank you.